Hello everyone, welcome to lecture 8 of the lecture series. Today we'll be discussing optical coherence tomography, both the theory, like different types of OCT, optical coherence tomography, also it has an acronym OCT, and be discussing different types of OCT and its theoretical foundations, and along with a lot of biomedical and clinical applications. So recap what we discussed at the very end of the previous lecture. Uh, so the primary goal of OCT is to get depth information, and at any point or any pixel on the sample, you can get a depth scan, also called the A scan. And by putting together a bunch of these A scans, you can get what's called a B scan. So it's a two-dimensional XZ cross section. And if you do this and scan every point, you get three-dimensional data, okay, also called a T-scan. So this is the this is how you can construct 3D volumetric images of the tissue samples or samples of epithelium. So last time we looked at the principle of what is called time domain OCT, and the idea here is that you have a source of light which does not have one wavelength but multiple wavelengths, a broadband source of light, and that is incident on a beam splitter which splits the light into the mirror and the sample arm, and you keep moving the position of this is called a reference mirror. Keep moving the position of the reference mirror and make a measurement at this detector, and you get an interference pattern which basically looks something like this. And the location of this burst corresponds to the location of the, like wherever there is reflection or scattering in the sample. And that this is basically how time domain OCT works. I'll kind of elaborate on this and continue like explaining a little this in more detail today. So the next thing is, so instead of it there being one layer or one reflection from inside the sample, one scattering event, if you have multiple layers of tissue, then from each layer you get this kind of a interference pattern, and so therefore at one location you get one interference pattern, another location you get another interference pattern. So you can put together these interference patterns, and that way you can measure the depth. And this is a function of like the movable mirror position. So 0 is here, D is here. So at different time points you get back to the distance positions, you get different signals, and this is essentially how you get like depth information in OCT. So let me kind of explain this a little bit further and elaborate with an animation. So let's say you have a reference mirror whose position is changing. Okay, this is the reference mirror. You're scanning the reference mirror position up, like in one direction, let's say for now. Okay, and for every mirror position, there is a detector over here. We call this photodiode. Like there is a detector which for every person make measurement. Next person make a measurement. Next person make a measurement. So as a function of that, this difference you keep making a plot of the intensity that you measure at the detector, and the shape of this pattern looks something like this. Okay, and this is essentially like this tells you the location. This position here tells you the location of the first of scattering, second scattering, third scattering, and so on. The crucial thing here is that this one burst of like kind of this oscillation, like this speed, like shape, this wave pattern that you measure at the detector, like corresponds to the one location. And as you can imagine, this width we call this delta z over here, delta z or delta z. That imagine if this pattern comes closer and closer, at some point it will merge with this pattern and you cannot distinguish the two, right? And therefore this delta z or delta z is essentially a resolution. let's say you have one layer and another layer. If they are very far apart, like the bursts are far away and you can easily separate them. But if they are close together, then the burst of one and the burst of the second one almost overlap with each other. And therefore, if the limit of when just when you can barely separate the two is called the limit of resolution, or in other words, the resolution, and this is the Z or Z resolution. So that's also called the axial resolution of OCT. We'll figure out how to figure out what is the value of resolution, what determines the resolution, and all that in the subsequent slides. But the important thing to notice is that because one layer gives you this one kind of a pattern, you like the whether or not you can distinguish one layer from the next is decided by how broad this kind of pattern is. Okay, and if you look at the animation over here, once you start, notice that whenever you hit the reference mirror, it hits a layer. So this is a layer 1, layer 2, layer 3 inside the sample. As soon as the reference mirror crosses that layer, in the detector you measure this burst of signal. So notice, like if you keep looking at this, the mirror is moving, and whenever the mirror position matches the sample layer position, you get one signal burst here. Next position, you get another burst here. Next position, another burst here, and another one here. Okay, this is actually how you collect data in time domain OCT. Sweep the mirror, collect data at every position. You get this pattern, and therefore you know that the layers are here, 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 here. So you can do some data processing on this to get the positions of these layers. And then this is for one pixel. You move the pixel, do the same thing, move the pixel, do the same thing. And this is done quite fast, but I'm explaining it slowly, but essentially you can get that sort of like you can do it at like 100,000 times per second, like 100 kilohertz or 200 kilohertz. With that many pixels per second you can select. So it can be done reasonably fast now. Okay? Any questions? Okay. So like why do it this way? So if you look at like in the next few slides, I'll talk about a brief history of what has happened in OCT and from the early stages, and what is the other idea people had to do this. Like what is good about this? Why does this work whereas something else is more difficult to do? Okay. So one of the first things that so you want to measure depth, right? So one way to do it, like if you think of it as say what happens in radar or ultrasound sound signals, right? Or even radar signals. You send a burst of a pulse out, you get it reflected back, and like you can by measuring the time, you can measure the distance. That is one good way of measuring like depth. But the thing is, it does not work for OCT. Why do we have this moving mirror and something else in order to for OCT? Is there a good reason for doing it this way rather than some other way? So the answer lies in the fact that we want to do like microscopy. We want to look at biological samples, and we look at small scales. So we want to look at something which is like 2 microns or 20 microns, something which is very, very small. So if you look at meters and kilometers, then sending a pulse and it will take some time to come back and you can measure the time. But the thing about that unlike sound, which travels relatively slowly, you don't think of it as slow, but 300 meters per second or something of that sort is reasonably slow compared to speed of light, which is 3 times 10 to the 8 meters per second, right? If you remember. So what does that mean, like in practice? So even in 1 nanosecond, 1 billionth of a second, one very small amount of time, like light travels this big of a distance, about 30 centimeters, 0.3 meters. So basically, light travels this distance, such a large distance in a nanosecond, a very small amount of time. Nanosecond is very actually not easy to measure. You can measure it, but 30, and there it travels 30 centimeters. Imagine if it has to be microns, right? Or so you have, they have picosecond, not even nanosecond. It's 1,000th of a nanosecond is a picosecond, and even less than that. So you have to measure time. If you want to measure how much time it takes for light to come back, you have to have essentially like a clock, a timer which measures like fraction of a picosecond or something of that sort. So the basic problem is that you don't have detectors of that sort. Therefore, time measurement, although it works for big scales or for sound, it just simply doesn't work. This time measurement. So what is the idea that people came up with? One of the ideas that one of the ideas is in trying to make these very fast measurements, because it's like just simply don't have the detectors, and the electronics don't work so fast. So what do you do? So another kind of that's where the idea of interferometry became like very interesting. So what's the idea here? One way to think about it is you send a pulse, but you can't measure the time back. What you do is send a pulse, split it into two, send that and send that like pulse in one direction, send another pulse in another direction. There is a mirror which reflects it back, and then there is an unknown distance which you are trying to figure out. Now the thing is, if these two pulses come back together exactly at the same time, then they constructively interfere. They interfere properly, and you can measure high value of a signal. If one comes first and then the other comes much later, then they don't interfere constructively. So you don't get that high signal. In other words, this one distance, which is the distance from the from you to the mirror, that distance is known. There is a second unknown distance. Keep changing the position of the mirror. Whenever it matches, you will get a signal. So basically, instead of making time measurements, you make distance matching measurements. So you send to the pulses and bring it back, and if the distance to the known, the known distance, which is the mirror distance, is the same as the unknown distance. So you know the unknown because you measure one, you know the other, and that's essentially the idea. So instead of making time measurements, you make a comparison measurement. And comparison, you can do it slowly, you don't need to do it fast. In your own time, you can move the mirror, make a measurement, move the mirror, make a measurement, right? So you can do it as slowly as you like. So the time constraint is gone. And that is the beauty of interferometry. You you don't need to measure time. All you need to do is measure the distance. And distance you can control in however precisely you want, whatever way you want. So that's essentially the underlying idea behind OCT. So people actually, the very first measurement actually tried something of that sort, where they took what's called a femtosecond pulse, a very short duration pulse, sent it, split it into two, sent it through one arm and sent it through another arm, bring it back, and both of them go to what's called a nonlinear crystal, and then if the lengths match exactly, then you get a nonlinear process, and so basically you get some kind of new frequencies being created, and you kind of measure that light, and you can figure out that whenever this matches this, you will get a signal. So that way they measured in fact inside the eye, how to measure distances and so on. This is the kind of the old generation of the first attempt to do OCT. And people later, when they figured out this requires complicated, so femtosecond laser, for example, is a very, very hard thing to. You can still buy them, lasers of this sort. These are very short pulse lasers, and they are very expensive. Crores, 5, 10 crores kind of like, so it's not practical to do this in a everyday kind of hospital or any kind of setting. It's like way too expensive, and it's also very difficult to do because of all the complexity of some of the optics. So the another advantage of like the kind of interferometry that this is called low coherence interferometry. The kind of the simple light source splitting into two and moving one and getting the data from the other is much cheaper. Okay, and yeah, sure. Correct. That's an excellent question. Yes, that is why if you use one wavelength, it can interfere constructively at lambda, 2 lambda, 3 lambda, and so on, a path difference. But if you use a second wavelength, then that is, you will be 0, lambda 1, 2 lambda 1, 3 lambda 1. And if you have another wavelength, so like at only at the 0 position will all wavelengths interfere constructively. They will they will wash away, destructively interfere at all the other positions. That is exactly why you can't use a narrow band or one wavelength phases for OCT. That's the reason why you need light which has a large range of wavelengths. In fact, the more wavelengths you have, the better. The more localization, the better your resolution will be. We'll see that later, but that's a good question. Do you get what I'm saying? Yeah, that's an excellent thing to think about, because if you think of when constructive interference happens, if just one wavelength, it will happen at like zero zero part difference, or shifted by lambda or part difference, or 2 lambda. But like for it will be a different set of like shifted by different amount. So like as you go away, only when this all of them interfere constructively at 0, when the distances are exactly the same. If you move it, then some interfere constructively, some interfere destructively, some in between, and so they will kind of average out to some constant. Okay. Good. Any other questions? Sure. Yeah. Please. A question on that. Say that again. Repeat the question. Sorry, I can't hear you. Why? Yeah. So low coherence or short coherence. So coherence here means, so so when light is coherent across a certain distance, it means that there is a phase relationship between the different points in here. In other words, if the shorter the coherence length, this is called delta, which we'll get to like the precise little bit more detail later. But basically, the coherence means this how much of a distance is this interference shape happening. Okay, what is the length? Shorter the coherence length, the shorter the better the resolution. So because you imagine if there's one layer and another layer, right? So if you have a short coherence length, then this particular shape here will be narrow. Okay, that is inversely related to how many wavelengths there are. Okay, and it's called Wiener-Khinchin-Einstein theorem. So that's the mathematical relationship. So it turns out that how many wavelengths are there? So like if you have, I told you that instead of one wavelength you have multiple wavelengths, right? So what is the range of wavelengths? What is the width of the spectrum? How many wavelengths you add up is inverse. Like the more frequencies of wavelengths of light you add up, the shorter this coherence length will be. Okay, so the coherence length determines your resolution along Z, and therefore you use low coherence light, which is large bandwidth light. not just one band, one wavelength, but a large range of wavelengths. The larger the range of wavelengths, the better it is. Okay, so that's the reason why. Yeah. Does it answer your question? Okay. All right. Any other questions online or here? Okay. So, yeah. Therefore, if you use a broadband beam and do this measurement, so if you have just one wavelength, it looks like this, and there is interference at all positions. But if you if you have short coherence length light, then there will be only one burst, and that's at the position where there is a maximum. And this way, you can kind of scan the reference arm position and get a depth profile. And so this was an extraordinary achievement um, in James Fujimoto was the professor at MIT who figured this out, or at least was his is the most cited version paper. There are a few others who had similar ideas, but this was in fact after this it was the field was revolutionized. Like now it is it's used practically everywhere. Okay, this is the working principle of what's called time domain OCT. There are a few other versions of OCT as well. So after there are a few other improvements. So this is the basic idea. Based on this, there are a few other improvements. I'll talk about them a little later in today's lecture. But there are another innovation that they brought about was instead of using like the beam splitters and stuff, you can use all fiber optics. So, fiber optics was developed previously for telecommunication, like for long distance transmission of communication signals and for internet and other kinds of things. But people in the biomedical community realize that because they are flexible, there are a lot, and there are different devices. You can have what's called a coupler instead of a beam splitter. You can have a optical fiber device which splits the light and then combines the light and so on. So you can buy stuff which was meant originally for other purposes, the communication system. So that's in fact, like a lot of things in biomedical is like it was invented for something else, like signals or communication or measurements before, and they adapted to this or and for astronomy, like things of that sort, or for satellite communication. And by the same token, people who do satellite communication also or other fields, if it is made for biomedical, they adapt it to other fields. So it goes back and forth. So there is, if you understand one thing, it always helps to kind of adapt it to another. You don't need to reinvent all these devices or reinvent these things. You can pick whatever other people have figured out and build on that. Maybe I have made it for big scale, you make it for a small scale, that microscopic thing, and so on. So there are ideas so that's the reason why having a rough sense of what's happening, even if you don't work in a particular field, what other people are doing in other places, if you should have a rough idea of what is going on, what is the latest, what are people doing, because it will help you in solving your particular problem. You can adapt whatever they learn into your field, and that's often how innovation happens. Yeah. So you can use no current source. You can use fiber optic couplers, fiber optic cables, and you can put it into a reference arm. You put it into a sample arm, and then you can have a scanning mechanism. This is called a galvo scanner or a lateral beam scanner. So whatever method you get one depth position, you get a picture. You move the scanner, and then next pixel, next pixel, next pixel. So you get a scan like this. And once you get scan like this, then move and scan like this and move scan. So you get XZ, the cross section, and then depth. So basically XYZ, like completely you can get volumetric data after this scan. Okay, so yeah. This illustrates that point. So get one scan and next scan and next scan and put them all together in a computer and get what the scan XZ scan. Okay. So this is essentially how OCT works. So the earliest, any question? Sure. Yeah. Yeah, the inside of the eye. I actually have a few slides. In fact, like the next slide I had was about the eye. Yeah, so I'll get to that now. Yeah. Okay, so yeah, in fact, I have a bunch of slides about the eye, which are, so so as you can imagine, this OCT is now like the clinical gold standard for a lot of like several diseases, especially diseases of the eye. So it's like if you go to a doctor in a big hospital and if you have some eye problem, often they do they use a slit lamp and they see like put some light and see inside what's called an ophthalmoscope. That's one of the things that they use to see inside your eye. After that, they use an instrument. I'll show you a picture of what the instrument looks like. Some of you might have even kind of been there if you have had an eye problem or some family member had an eye problem. But basically, you can see the inside of the eye. So these are older kind of, you can get much better images than this, but this is one of the early OCT imaging data where this region here is called the retina. Okay, that is where like the light falls on the eye, and that's actually where you see that's the photosensitive, the light sensitive areas in the back of your eye. So you can think of your eyeball as a sphere. In the front, there is like a lens and like something which allows light to go through. And in fact, the iris, like sort of, you can like the eye has muscles which kind of contract and expand. So if you're in the dark, it will expand so that a lot of light comes in. If you're in a bright light, it will contract so that only a little bit light goes in. And then you have a lens there which focuses the light onto the back of on the retina. Retina is where the image, the picture of what you're seeing outside, an image is formed in this retina. So this is where you can actually see. Vitreous is the liquid in between, which is the transparent liquid where the light goes through. It's not air, it's liquid between like kind of the lens and the retina. And there are several different regions of the eye which you can clearly see. And this is like a cross-sectional image. It's like you're getting a if you like imagine virtually if you cut the eye, what would you see? That's essentially what we are seeing here without actually doing any cutting. You can imagine how this is useful, right? Because you are actually getting images as though you are cutting the tissue without actually cutting it. And that's the big advantage of OCT. And so, in fact, for like say a rabbit or for this, so yeah, this is actually human. Like after, like say, like after you have donated your eye, you can actually get. So this actually after a person is dead, you get the eyeball, cut it, and actually see. So they did OCT before cutting, and then they actually cut the eye and actually saw what it looks like. And you need to do this because in the beginning, you want to know if what you're getting is real or is like some kind of made up thing. So this data shows that there is a good connection. So you can see if you actually cut, it looks like this. If you don't, like if you do OCT before cutting, it looks like it. So there is a good match between all the different layers and regions, and therefore it's good, like it's reliable data. Yeah. Mm-hmm. Yeah. Any number of layers depend. Like so, typically, if you have you can choose like sort of you can get one layer, and depending on the resolution, you move so that like you basically do sampling in such a way that at Nyquist rate, meaning you get one, say the size of the pixel is your resolution is about say like, uh, 10 microns. Okay, move 5 microns, get another image. Move 5 microns and get another image. If you can get that even like 1 micron spacing. but you just do oversampling, right? If you get at 100 micron spacing, you're losing data in between. So you basically do sampling in such a way that you just enough sampling so that you can kind of you can cover the full area. That depends on the resolution of one pixel. That's how you decide how many, like how many slices to take. Okay? Does it answer your question? Okay, thank you. Yeah. So yeah, so in the early stages, people did this a lot, meaning they actually did OCT before cutting the tissue, then cut the tissue and look if the data you get matches the cut tissue very well. And it turns out that this data is another kind of a data set where this is a human artery, like in the heart, right? So kind of as like that goes from the like which takes blood from the heart and goes out. So you can cut and you can cut with cutting and without actually cutting, but doing OCT, they were able to get good like kind of correlation. So they look almost the same, which means to say from OCT is actually real in a biomedical sense, meaning yeah, like instead of cutting, you just do this and it will work. That's really the bottom line here. So this is the first like proof of concept saying that this basic idea of OCT is useful for clinical applications where without cutting you can get this data. So you don't need to do surgery or do cutting or anything of that sort. Yeah. So another kind of image of the eye. So this is like if you look from the front with a kind of instrument, the eye looks something like this. If you take a cross section along this white line over here, it looks something like this. So for example, this is like this is in fact like in human in a person without actually like in vivo, meaning the person was alive and you did the like imaging while the person was sitting in front of you, in front of the instrument. Okay, this is the previous one was a dead like sort of it's after the person died, you take the eye and cut it and see. But this one is, of course, there is no corresponding cross-sectional image, but this is actually a live person. You can get images from inside a live person. That's the first demonstration, or one of the first demonstrations of that sort. And we can actually see, for example, so this is the retina over here, and so you can also see the like what's called the fovea over here, which is the like this place is the location where there are most number of rods and cones, most number of sensors inside your eye. It's where you can see the best. In fact, most of the time when you move your eyeball, the light falls like the best image will be at this what's called the fovea. Okay. Another thing is this what's called the optical disc. This is also called your blind spot. It's the place where the optic nerve goes down this way. So there are no sensor, like no kind of rods and cones at that location. So that's why you like if light falls on that location, you just cannot see it. Have you heard of the blind spot? It's so like in fact there are like kind of cool like you can on YouTube you can take a look. There is if an object is kept in some place like sort of if it is at your blind spot, you literally cannot see that. Like you have to turn your eye to see it, but with like light if light hits this location, it cannot actually visualize it, and you cannot see that particular object. It's you're blind to something which is light falling on that area, and it's so you can see these kind of features in the eye for the first like kind of with OCT, which is very useful. Not only that, you can see how thick the thickness of the retina. There are features of the retina which you can see with this kind of an image, and like in some diseases, the retinal thickness could be an important factor. And so, like you can actually measure how thick the retina is at different locations in your eye. In the back of your eye, places it has to have a certain thickness in different regions. And so the doctors know what it should be in normal. So this is say a normal person. Then in a diseased person, they'll do a study. Like they'll take what is they'll do what's called a randomized control trial, meaning like they'll take say 1,000 people normal with normal eyes, 1,000 people with a particular disease, and then they'll see measure the thickness of the retina, for example, in normal. Like why not just one? Why 1,000? Why do you think you need to do actually 1,000 times? What do you get? What's your guess? Sorry, precision in what way? Yes, but what can you elaborate on that? So the idea is each person's eye, there is natural variation, right? From one person to the other, there is some variation. And therefore, even in a normal, what you think of as a normal eye, it may be a younger person, shorter person, taller person, fatter person, like or bigger eyeball, like whatever reason, right? Like sort of. And so basically, there is variation naturally. So, like you measure it 1,000 times to get an overall average and with a kind of variation, like the kind of standard deviation, the variation in the normal eye. Then, in a diseased person, then how is it statistically different? Meaning, so if you have one set of measurements, like let's say it's like sort of the distribution will have like some maybe the value is like say 0.5, 0.4, 0.6, like sort of there may be a distribution for the thickness, say for example. So if it is abnormal, maybe the variation is like sort of here. So it actually be 1.0. So the whatever after doing some calculations, they measure come up with a measure. And for all normal people, it's not exactly one number, but some range of values. But for disease, it may be another range of values. So the question is there enough of a difference between these two? In another case, it may so happen that for normal people, let's say this is the same distribution, but for abnormal, it may just be like this. And there is a very big overlap between the normal and the abnormal. In that case, that cannot be used as a good measure of disease. Like that measurement is not allowed to be because normal and disease, like there is a range of values for normal, there is a range of values for disease. They are so much overlapping so much that you simply cannot distinguish the two. That's why you need to do it, and a lot of patients can actually figure out because their inherent variations could all like tell you if the distributions are far apart, then you have a like method of diagnosing a disease. If the distributions are very close to each other, then that is not a good way of distinguishing, diagnosing that disease. So that's basically the idea. That's why you do this kind of study, like with lot of people and different kinds of like control for as much as you can. And there are like people who do statistics actually have studied this kind of problem. There are statistical tests which say, are these two, like the normal and the abnormal kind of distributions, are they very sufficiently different? How different are they? There are statistical measures of this which people have come up with, and so we can use that and do a study of this sort, and that will actually tell you, like kind of give you like kind of this is how people have figured out OCT is good for this disease, OCT is not good for this disease. So the way you figure it out is do this kind of a study and then figure it out. I'm just giving you a rough sense of the kind of, there are nuances and details, but like this is the basic idea. Okay. Yeah. Any questions? Okay. The next thing is, so another feature of OCT, which is related to the wavelength, is that how deep can you go? So, as I've discussed in previous classes, the longer the wavelength, the less scattering there is, right? And therefore, the less scattering there is, the deeper the light can go. If light scatters away from the top, then it doesn't go to far below. Okay, so if you use 1.3 microns or 1300 nanometer light, which is longer wavelength, you can get deeper images. And if you say 850 nanometer wavelength, You can get shallower kind of, this is the range of wavelength images you can get. So this is what's called the, this is called the human epiglottis. It's basically, if you can imagine in your throat, there is some kind of a flap, like something which, if you swallow food, what prevents it from going into the windpipe, into the lungs? So this epiglottis is the thing that moves, so that when you're swallowing, it stops the food from going. When you're breathing, it allows the air to go. So this epiglottis is the thing that is almost like a valve which directs food in one direction only. So yeah, so this is a cross-sectional image of that kind of a epiglottis. And here, if you use OCT of one wavelength, this 850 is like I'm saying one number, right? But it's actually a broad range of wavelengths. This is the central wavelength. It's the few wavelengths. There are few wavelengths before, few wavelengths after. So if you use wavelengths around 850 nanometers, you get some amount of penetration depth. But if you use like longer wavelengths, you get better penetration depth. What's the disadvantage? The disadvantage is that the resolution will become worse. So you'll get deeper data, but the resolution will not be as good. The exact relationship we'll get to in a few, like a little later today. But basically, this is kind of the trade-off you make. So you can see inside and you can see deep inside by choosing different wavelengths of OCT light. You can choose how deep you want to go and what resolution you can get. So these are kind of things as engineers, and if you want to design an instrument, you have to make these decisions, choices of which type of laser to use, which type of system to use, what bandwidth, and so on. And so this is another example of cancer versus normal. So this is normal colon. Colon is a part of your large intestine, and this is where the food goes to. And so in normal, so this is what's called histology. This is OCT data on the top. If you actually take the tissue, cut it and put some chemicals on it and see, a doctor can see this. So these are actually physically cut ones. This is without cutting with OCT, with 3D data. So you can see like there is a connection. So the resolution here is not as good as this, but you can still see a lot of what, as long as you can see the important things, you're okay. So this is normal colon, and this is what's called adenocarcinoma. It's cancer, cancerous colon. So the crucial thing here is that there is a big difference in OCT. You can see a big difference between cancerous colon tissue and normal colon tissue. It means that this OCT can perhaps be used for cancer diagnosis for colon cancer. Okay, you can build images and systems and devices which use this fact that there is some difference, visible differences in OCT data between cancer and normal. Therefore, we can build an instrument which can go into the colon and see if, look for this kind of images and get data and diagnose diseases. So these are some examples of the different medical applications of OCT and how it could be potentially used. I'm going to give you a few more examples in the next, in a minute, okay? Especially the eye and stuff. So there are different kind of scanning mechanisms. There are different approaches which you can use for making OCT measurements. So in general, what they have in common is you have a light source, you have like a fiber optic component, and then you have a 50-50 beam splitter, which can also be fiber optic. One goes to the sample arm, which is where you the person is or tissue is. Then other goes to the reference arm, where you have a mirror position which can be adjusted very fast, like high speed, what's called a high speed delay scanner. So it moves the mirror position very quickly, and you get data as you move this mirror. And then you have a detector, and you have some filtering and demodulator and stuff, and then it goes to a computer for data and image processing. So this is essentially how a lot of these kind of systems are built. This is like a rough schematic for a lot of these kind of systems. And So if you go to a hospital, eye hospital, this is the kind of OCT system that you will probably see. So where in fact like your head goes somewhere over here. So you put your chin on top of this place here. You place your head over here, and the OCT system sends light in this way, and the doctor sits on the other end and kind of looks at makes sure you have positioned the right way and they're not blinking and so on. Then they can get an OCT image of the inside of the retina. So they basically, if this is the eyeball, then there is a OCT beam comes in. There is a mirror which is a scanner. So basically, you can scan this mirror, and that goes to different positions in the eye and gets an image at every pixel. At every position of the scanner, you get a axial scan, A scan, and you put them all together in a computer and you get a full image. Okay, so you can, this is roughly how the instrument is made. And when the doctor looks at, the doctor will get an image of this sort out at the other on the computer. And this is again the retina. So inside the eye, you can actually measure, so the thickness of the retina and stuff is basically you can, like the computer, if you do some image processing on this kind of an image, you can get thicknesses, how thick it is at different positions. So as a function of position, you can get the thickness of the retina. It's called a thickness chart, and this is in micron. You can get a thickness chart, and in fact, you can convert this to an image of for different regions of the eye. You can plot the thickness of the retina at different locations, and like a doctor can look at this kind of a image and say, okay, they can even give you averages, an average here, average here. So in different kind of these regions, what are the average thicknesses? If it is a normal eye, you have some range of values for these thicknesses, or you can look at this color chart and say the red is like very thick, or yellow is like you can kind of you can convert this into a color kind of. Black is zero thickness and 500 is maximum thickness. Red is maximum thickness. So different colors you can correspond to different thicknesses. So you can actually visualize the profile of thickness of retina, and the doctor can look at this chart and immediately say, oh, this is there is a problem here, or there is a problem here. The thickness will become too less, or whatever the disease may be. So this part of the eye is damaged. Whatever exactly has happened, the doctor can take a look at this kind of an image plot. And so as engineers, one of the things we have to keep in mind is not only should we get some data and make it kind of just getting data is one thing, but presenting it in a way that doctors would find useful is an important part of actually making, as engineers, we forget or we kind of don't pay attention as much. And one of the important lessons that all of you should kind of take away from this lecture is that if you build any kind of an instrument, unless you make it so easy to use for the doctor or any end user, it's unlikely that they will use it. And if it's unlikely that you use it, however good your technology is, it simply won't make an impact in the world. If people simply not use it, if you don't make it as convenient as possible, you can get all this sort of it's not difficult in some sense, converting this kind of a chart into a circular chart with like a color bar or whatever. It's a different way of visualizing the same data that you have already collected. But if you show doctors the data in the way that they can understand and interpret very easily, and if it makes their life much easier, that is really the only way in which you can actually make real world impact. Always keep that in mind, because this is often, by engineers, it is often underestimated. To give you a different example, people say in MRI or some other engineers like this kind of this rainbow or different color map, but doctors who are used to seeing like X-rays used to look at black and white kind of grayscale images, right? When even though engineers thought color images have much more information, they look much better, it's easier to see. doctors were only used to looking at black and white images. So they had to convert the color ones into black and white so that it's much easier for the doctor to recognize. So it's like it's counterintuitive. As engineers, we think, oh, we are giving more information by using color or something of that sort. But making it easy to doctors is far more important than kind of you what you think is kind of the best, nicest thing to do. So just that those are kind of practical and like once you show it in the right way, then people doctors will are much more likely to use it and make it useful for patients at least. So that's an important lesson to keep in mind. Yes. Which one? This one is micron, the thickness of the retina. X-axis is the position along this direction. The A scan, so 0th A scan. So this is A scan number 0, 1, 2, 3 up to 500 or so roughly. So basically different A scan positions on the X-axis. Y-axis is the thickness of the retina in micron. Okay. Any other questions? Any questions online? Okay. All right. Another version of OCT which is also very useful is what's called endoscopic OCT. So endoscopy is basically where you take something that looks like a thin tube, and if you want to see the inside of some organ, it's common. It's doctors like typically say they put like a optical fiber bundle or a camera at one end and put the camera inside to see inside the body. It's like a thin tube where there at the end, like there is some way to get images out of it. Like you can have optical fibers or you can have like cameras or whatever the mechanism is. So typically optical fiber bundles are used. And so like you can basically it's like going and seeing inside, like it's movable, it's flexible. You put this in and you can see inside different organs, different parts. Okay, but this is regular. What's the advantage of a camera? You can see, get images. What's the disadvantage? You can't get 3D. You get only surface information, right? The thing about OCT is endoscopic OCT, which is basically the combining this OCT with endoscopy. Instead of getting a regular ordinary camera, you put an OCT imaging like system there. Like the end of an OCT system, the sample arm goes into that endoscope. And what it means is that you get 3D images from inside. Instead of getting surface images, you can get deep inside. You can see and visualize the side of different organs and figure out what is going on. I'll show you a few examples in the next. So basically, so this is the kind of construction that you typically do. So this is like an optical fiber, and you have like some kind of protective, like something layer on top, because optical fibers are very fragile and thin. You want to put something around it, and then you also have a lens system, shines light on the side, and you rotate. If you rotate this, then you can get a circular image from all the different sides. Okay, so this is and so this is like an example of how this is the basically this is the optical fiber here, and then this is the lens here, and then light comes out from this end. This is kind of how it's works. Okay, and from this you can get images of the esophagus, the food pipe, from the whatever connect when you swallow food, what goes from the mouth to the stomach, that connection is called the esophagus or the food pipe. So you can get images of the different layers of the esophagus, cross-section images. So instead of just getting the surface of the esophagus with a camera, you can get 3D images from deep inside different layers of the esophagus with this kind of an approach. You can see small details in different layers, and people have looked also at taken a cut, actually cut it and see to see if there is a connection. And so later I'll give you an example of how this could be useful for finding esophageal cancer. So if you have cancer of the esophagus, then you can actually see different layers of cells inside the esophagus and figure out if there is normal, if it's not normal, and so on. So that's basically the idea over here. This happens to be a rabbit esophagus. This is one of the earlier studies that was done. And same kind of OCT can be used for ultrasound, compared to ultrasound. So previously, this is for the heart. So this is for the human heart. So this is ex vivo, meaning after the like person has died and you kind of after like autopsy perhaps. So you can get so if you want to visualize, say if a person died of a heart attack, so what happened? Like if you want to figure out what actually caused the heart attack, was there a blockage somewhere or things of that sort, to see the inside of the arteries, so you can like put endoscope like device and see like move it around and see where the problem was afterwards, to figure out exactly what happened and what is, like maybe for another patient you can save their life. So the old version of doing it was called IVIS, like so in vivo ultrasound. So it basically you can actually ultrasound was where you can get depth information, right? So you can, they made endoscopes with ultrasound. But the thing is, because sound waves have long wavelengths, so the resolution you can get is quite poor, as you can see. Compared to OCT, you can do the same thing with the OCT endoscopes, and you can get much higher resolution images of the artery, for example. So this is a very good way of figuring out um, what the problem is inside the heart and so on. So this was like for ex vivo, meaning like the people had had died, but like there was an important breakthrough where they did it in living. Like so, this is in like this was a human artery in vivo. So this was inside a patient who was under a surgical table, like inside a surgery operation theater, and like they actually did this OCT. And so in fact, you can see these regions over here, like in some places here, these things here are actually a stent. The person had previously had heart attack, and like the doctors had got it. No, does anyone know what a stent is? Stent. No, it's okay. Some if you know, so basically, if they say a blockage, so heart surgeon will go inside, put something like a metal kind of wire. They'll put it and expand the wire so that the blockage is unblocked, and that is called a stent. So the metal kind of wire, like insert something like a metal tube kind of a thing, and make it expand so that the blockage is kind of released essentially. See so you can visualize the stent, if the stent has been placed properly, if it's in the right, like in the right location. Like you can see, how do you know if you've done the right good job of doing the stent surgery, right? So you can use a OCT to figure out, get an image of how the stent is placed and what, like if there are any issues and so on. Okay, so that's another use or advantage of OCT. Question? Okay. Maybe in a few minutes we can take a break and just yeah. So the crucial thing here is that like you can build different kinds of OCT systems. You have a choice of what type of imaging systems you can build, and the resolution of the OCT is something which to some extent, which is in your control. By choosing the right range of wavelengths, by choosing the right optics, what is the numerical aperture, how like tightly, what is the focal length of your lens or numerical aperture of the lens, and by choosing some of the optics parameters, and you can basically figure out, like make a high resolution system or a low resolution system. So it could depend on what is. So you don't want to build something which is the highest possible resolution if you don't, like if the disease does not require that you build a high resolution system, you may not need it. But if in case for some diseases you need a high resolution, then you can build one. Often it's more expensive and more difficult to build, but that's the kind of engineering trade-off you have to make and decide what kind of system you want. Okay, and typically you can use low NA, low numerical aperture, and get much larger depth, ranging depth. So how deep can you go is also determined by what lens you use. If you use a high resolution lens, high NA lens, then the depth you can get information from is shortened. It's in fact what's called the Rayleigh range. I'll get to that a little later, but basically there is a connection. If you get high resolution along spatial, so there are two types of resolution in OCT. One is spatial resolution, other is axial depth resolution. Those are two different things. Okay, XY resolution, if you can make it smaller by using high NA. If you use low NA, you'll get bigger XY resolution. And then that means along Z, you will get smaller range of Z if you use high resolution like in OCT. But if you use lower resolution along XY, you can get much bigger Z, much bigger range for Z. Okay, that's the trade-off which you always have to make. So like 0.05 and NA of like something like 0.05 is lower NA. Okay, NA of like 0.2 or 0.1 or something of that sort is fairly high NA. In OCT, that's kind of those are kind of relationships. So I get to the point of this resolution and so on. I'll get to that in the next a little later. But this is the crucial trade-off. So if you want high resolution OCT, people have built those kind of systems. So this is like high resolution OCT of the eye, and so you can, in fact, the fovea that I mentioned and of the eye. So this happens to have a 3 micron axial resolution, so which is a very high, relatively high resolution along the Z direction. And this is the OCT of the normal human retina, like sort of a living person, a normal eye. These are high resolution images. You can even see finer details. So some of the other layers of the eye, which were previously like it's all blurred, now with higher resolution, you can get much more fine details. If this is important for diagnosing a particular disease, then you can use this high resolution version of OCT to get good, much better data. Okay? And here is people have also built high resolution versions of the endoscopic OCT, where you can get much higher resolution images than before. So this is like the endoscope, like I mentioned, the camera, right? The camera view, and you can put like this OCT fiber, like it's very, very small and thin. And this is the scope. This is like goes in the inside of the endoscope. You put this OCT. So the tip here, really, the OCT is only at this very tip. Like the light comes out from the very tip over here, and you can get images of the different regions of the at very high resolution. You can get endoscopic of the food pipe or different kinds of different organs. You can get very good high resolution images, and from this you can do diagnosis of different diseases. This is a good time to take a break. When we come back, I'll continue our discussion of OCT, but the time domain OCT is one version of OCT. A few others, which is the next thing I'll discuss.